Danny Hamel, who did his PhD at University of Waterloo. One of his supervisors, Kevin Resch, who was a graduate student here at the U of T with Ethan Steinberg students. And then he went on to do a postdoc with Philip Walter at University of Vienna. He's now a professor at University of Moncton and the Canada Research Chair in Optics and Quantum Information. And he's going to be telling us about photon pairs to photon triplets today. So please join me in welcoming him.
Okay, perfect. Thank you very much for the introduction, and thanks everyone for coming to my talk today. Before I start, I'll just tell you a bit about where I'm coming from today. So Université de Moncton, so it's a French language university in New Brunswick. So right there on the coast, about 20 minutes from the beach. The warmest waters north of Virginia is how the board likes to call it. So it's a very nice place. It's actually the largest French language university outside Quebec in Canada. So that's a big qualifier outside Quebec, but puts us in first, so we'll do it. And so in our physics department, we have about 10 profs. The main research areas that we do is thin films and photonics. So on the photonics side, we have 4 profs, and I was thinking about it this morning. We actually have quite a few links with U of T. So we have Alain Haché, who did his PhD here with Henry Van Driel. So he's been with us for a long time. We recently hired Lambert Ginard, who's a new faculty. He did a postdoc with Jeff Landine, who's also a graduate from here I think with EFRM. And as you said as well, I'm 2 generations away from U of T. And here you'll see I've got another point here, that's Waterloo. And the reason is that, so John asked me to talk about my work on cascaded down conversion. And so instead of only telling you about the last few experiments, I'm going to give you kind of an overview of the history of what we've done in this field. And that started in Waterloo a bit over 10 years ago. So since I think this is so I'll start by telling you about the concept and some first demonstrations. I'll tell you about the first experiment that we did where we tried to basically show entanglement in the system. And then in the end, I'll tell you a bit about some applications that we've looked at or are looking at into how we can use photon triplets produced by cascaded down conversion. So this is a pretty, from my understanding, it's a pretty focused talk. So who here knows what down conversion is? Okay, so I'm good. I assume that I didn't need to go into it, so that's perfect. So you all know that if you have a pump, you can get photon pairs. We need to conserve momentum, we need to conserve energy. And then because those photons have correlations in energy and they're created at the same time, they have tight energy time correlations. And then we can use this to produce entanglement in various degrees of freedom, be it OAM, polarization, time bands, all this kind of stuff. So it works really well if we want to produce 2 photon entanglement. If we want to go to larger systems, then it's more complicated because we're producing pairs. So if we want to get larger entangled systems, you need to combine pairs in some way. One common way that's done is shown here. So here I'm showing how to produce one way of producing a 4-photon GHZ state. So the idea is that if you've got 2 SPDC pairs, the sources producing you Bell states, you can take 2 of the photons, combine them on a polarizing beam splitter, and then you'll get this complicated state at the output, which sometimes you have a photon in each output mode, and sometimes there's 2 photons that are in the same mode. And then what you can do is you can just post-select that you impose that you get 1 click at each of these detectors. That cancels out some terms, and then you get your 4-photon GHZ state. In this kind of procedure, the post-selection becomes part of the state preparation. You can't separate the 2. And that means that the state, for certain applications, that really doesn't matter, but for certain applications, that makes a difference. So if I show you this state, I tell you what can you do with it, you might say, well, I can detect 1 photon in the diagonal basis and I'll prepare a heralded GHZ state. But you actually can't do that. That doesn't work because you've already used up your post-selection. There's no single channel that you can use to herald the presence of a 3-photon GHZ state. So if it was a 3-photon state that we had here, you think you could herald Bell pairs. You can do that, but you need 6 pairs to, or 6 photons, so 3 different pairs to do it. And sometimes you might want to do like a quantum gate. Well, for quantum gates, sometimes you need to use post-selection to apply your quantum gate. Well, if you've already used up your post-selection to create your state, then you can't apply that quantum gate to it. So because of that, there was a lot of proposals of methods of how can you produce 3 photons directly, which is kind of the next step. So you can do this with a Chi3. A Chi3 where you only have a single pump, and then you can produce photon triplets with that. People have looked at up converting, down conversion. So you've got 2 down conversion pairs here, and then you up convert a single photon here. People have actually demonstrated photon triplets from quantum dots. And then there's some more exotic proposals that have been proposed as well. But what I'll be telling you about today is cascaded down conversion. So if you already know down conversion, then it's pretty simple to understand. You do an SPDC, you've got a pair, and then you use that photon to pump the second nonlinear crystal. And then you can get another photon pair. And this was proposed quite early. So in this paper, in one of the GHZ papers from 1990, where they talked about doing a Bell's theorem without inequalities, they mentioned instead of a direct down conversion to 3 or 4 photons. So this was kind of looking kind of like a Chi3. One could in principle contemplate a 2-step cascade of 2 photon down conversions to produce a 4 photon hexagon. So just kind of a throwaway line at the very end of the paper. And why wasn't this done for a long time? Well, basically rates. Down conversion is a fairly inefficient process, which means that it's hard to get a lot of counts out of this. And I'll talk a bit more about that in a bit. And then we expect to have, because these 3 photons are created from a single pump photon, we expect to get much the same energy time correlations as for pairs, but with triplets. So we have the sums of 3 frequencies that equal the frequency of the pump. So when you're talking about rates, if you look at, yes.
Just curious. Sorry. Of course, the sum rule is the same, but in general, the correlations probably aren't completely permutation symmetric.
No, yeah. And there's some work, I'll present a paper, not from my group, but from another group. It's looked at kind of all the different combinations that you can do, playing around with phase matching conditions and to get like separable states or getting them like in frequency correlated or uncorrelated. So if you take the kinds of sources that were available back in 1990, you had something like BBO with efficiencies up to say 10 to the minus 11 in bulk. Let's say you've got a detector here that's limited to around 1 megahertz, which is kind of an order, like reasonable order of magnitude. Then you can calculate how many photon triplets you might produce, and you can expect to get about 1 per day. And then let's say you want to do something with those photons, so maybe you want to detect them, and you've got not so great detectors from the 90s with 5% detection efficiency, which actually, if these are coming out at telecom wavelength, is not that reason. Is even like 10 years ago, this was kind of what people were using. And you want to do a Bell inequality, so you need maybe 200 counts, you need about 250 years. So if you want to tell your PhD student this is going to be your project, he's not going to be very happy, or she is not going to be very happy. If you move to something like PPKTP, you've got 10 to the minus 9 efficiencies. Then you can produce around 3 triplets per hour. Your Bell inequality is going to take 2.5 years. So maybe you can do a PhD project on this, but you better set everything up right from the start. If you go to waveguide PPLN, then you can produce on the order of 1 per second, and you can do your Bell inequality in around 20 hours. So this is getting to the point where you can actually do measurements. So having these high efficiency waveguide PPLNs really made a difference in making these experiments possible. So our first experiment on this, basically we were just trying to observe any signal. So basically measure photon triplets. So we had a pump laser at 405 nanometers that pumps a bulk PPKTP crystal, producing photon pairs. One of them's at 75 and the other one's at 840 something. You'll see this number changes in every talk, in every experiment I present, because it's always a slightly different crystal we're using. So it's just kind of the leftover. We detect that using a silicon APD. And then the 775 nanometer photon is sent through these PPLN waveguides, which produce 2 photons that are around 1550. And then we just use the fiber beam splitter to separate them out to 2 detectors. Because this is telecom and this is 15 years ago, these detectors were gated. So they were in-gas gated detectors because they have way too much noise otherwise. So we had to use the signal from the first detector to turn on this detector, and then the signal from this detector we used to turn on this third detector. So anytime there's a click at D3, it's automatically a threefold coincidence. And then what we looked was the time difference between this first and this last signal. And we found figures like this, which are very noisy. This takes about 20 hours to integrate. We get 5 point something triplets per hour. And we see we've got some signal that's time correlated. Now, when we measured this, we were like super paranoid because like the signal to noise isn't great. These APDs, like this one, when it turns on, when the gate first turns on, there's way more noise and then it kind of flattens out. So there's like a second peak that's not shown here. That's just like dark counts that at the beginning of the gate. So we really want, and then there's apparently, like we're thinking of conspiracies. Look, so apparently these APDs, when they detect a photon, they can emit a burst of light. So we're like worrying, well, maybe it's the burst of light that we're getting here and we're getting these clicks at these detectors. So what really convinced us was we played around with phase matching conditions. So we could control the temperature of these two crystals. So here we set it up so that we expect to get down conversion, and we do. And then we'll change the temperature of this PPLN waveguide to be in a regime where for the 776 nanometer pump, we should get no down conversion. And then we got the signal. And then we change this temperature to change the 776 nanometer to be 775.4. We expect to get the down conversion again, and then we get our signal back. So this was kind of the convincing argument that we're really, really seeing like the triplets. And I mean, the rates match what we expected to get. So like that also was very convincing. But there's no proof of entanglement here. We've got some signal that's time correlated, but you can get that classically very easily. So there's no proof that these triplets are really entangled at this point. And I should mention that other groups did related experiments in the following years. So Guang Kangguo's group in China did an experiment where they produced photon pairs in rubidium and then used downconverted one of those photons in a PPLN waveguide. And Christina Silberhorn's group in Paderborn, they did a chip where they downconverted. They basically chained two periodically cold systems on the same chip. But in both cases, the rates were lower for various reasons. In this case, their efficiencies are a bit lower and they're throwing away a lot of signal because of some spectral filtering that we're doing. This one, I think they just get like the coupling between the first source and the second source just hurts a lot. So we wanted to show entanglement, and I'll present to you experiments we did to show both that these systems had energy time entanglement and polarization entanglement. So first, we'll talk about the energy time correlations. So as I said before, we expect these three photons to be correlated in energy because like energy is conserved in the process. And we can see that as creating kind of EPR correlations. So you get the same thing with if you do a photon pair, you've got these systems that have sums of frequency that are highly correlated and differences in arrival times. And you can make this argument that this is kind of similar to having a difference in position and a sum of momenta that are correlated as well. So one way of doing it, you can actually just do like a photon, its position is kind of related to its detection time and its momentum is related to its frequency. You don't actually need to do that because you can also just look at time bandwidth inequalities for an individual photon. And then because frequency is related to time by a Fourier relation, you've got an uncertainty, and then you can build the larger inequalities from there. So we used, so Van Luck and Furusawa had generalized time bandwidth inequalities to tripartite systems, except their inequalities didn't have these parts. So they were just like one of these. And turns out, well, I think this was actually because of Ephraim. So we initially used those inequalities. And if I remember correctly, Kevin gave a talk, and then Ephraim commented that, what about if you have a mixed state? And it turned out that if you have a mixed state, that you can violate the inequalities of Van Luck and Furusawa. If you just have like two photon entanglement and a separable one, so this way, and then you have these two entangled and that one separate, and you mix that together, you could possibly violate the inequalities that Van Luck and Furusawa used. So they checked for full inseparability, whereas these inequalities that we generalize, they check for genuine tripartite entanglement. So it can't be just a mixture of two photon entanglement with these inequalities. So We want to measure these inequalities. So we want to show that we have tight energy correlations and tight time correlations. Now, we already know that we have good time correlations, at least for one of the terms. We'll need to go get that third one, or at least like a second combination. We need these energy correlations though, and that's a bit trickier because to measure this would be really hard to measure directly because we need a correlated spectrum of 3 different photons with like megahertz resolution, and these bandwidths are huge, like 50 nanometers for the 1550. So there's like no way that you could get this with high enough resolution. So we made this argument that, well, what we really want is just the uncertainty and the frequency of the pump. So if we have a pump that's very narrow band, we can monitor the uncertainty in the wavelength of the pump, and then if energy is conserved, then that should give us an idea of what this term is as well. So we switched our pump laser to be narrowband because initially it wasn't narrowband enough in the first experiments. We put a Fabry-Perot interferometer to monitor that bandwidth throughout the experiment to make sure that we always have a tight bandwidth. And then we added time tagging for the 3 photons, which allows us to get all the different time correlations that we need. And so our 2D histogram or 1D histogram that we had before turns into this 2D histogram, which is a way better signal to noise, but well, for 2 reasons. One is we've got a detector that has lower dark counts, but mainly because we're now expanding our dark counts over 2 dimensions. So that just gives us a much better way to remove the noise from our bin that we're actually using. And then we can integrate this in one direction or the other to get the time correlations. And we find that it's basically just dominated by detector jitter, right? So we have on the order of hundreds of picoseconds. And then our bandwidth, we monitor throughout the experiment, and it always stays around 6 plus or minus 2 megahertz. Then we plug that into the inequalities, and then we are more than, well, several orders of magnitude away from sectorability. The downside with this is that there's kind of a circular argument going on. So it's nice if you believe in that down conversion conserves energy. We've like proved that this actually, we have the tight energy time correlations. But the reason we think we have tight energy time correlations is because down conversion conserves energy. So it's not completely pleasing. And we did a bunch of measurements to like show that if you believe that down conversion doesn't conserve energy, like there's some results that we have that wouldn't make sense. But we wanted to have like a different way of checking the energy time correlations. And that's using, we did that using Franzen interference. So I don't know if everybody here has seen Franzen interference, but for a pair source, the idea is that you send 2 photons inside an unbalanced Mach-Zehnder interferometer. So each photon can either take the short path to detectors or take the long path. And the idea is that if both photons take the short path, that will look indistinguishable in the coincidence basis as both photons taking the long path. And therefore, the coincidence detections will depend on the sum of these 2 phases. And then in that paper from 1990 that I mentioned before, they actually mentioned like, could also do this, other things if we have 2 photon down conversion. We could do a 3 photon generalization of the Franzen experiment. So again, we're just stealing ideas from that 20 years ago and trying to do this 3 photon Franzen experiment. When you do a Franzen experiment, there's limitations on what you can use as your time delay, so how unbalanced the interferometers are. You want it to be more unbalanced than the single photon coherence time. That's because you don't want any single photon interference fringes. But it needs to be less than the pump coherence time so that you actually get 2 photon interference fringes. And you also need a secondary condition is that you need the time to be larger than also the detector resolution, because you want to be able to actually distinguish whether you had both photons take the long or short, so that when they're balanced, or compared to one taking the long and the other the short, or vice versa. So you want to be able to take those out. Now, so this one, basically for us, that means that meant we needed an interferometer on the order of 1 meter, which is a fairly large interferometer that you need if you want it to be stable for 20 hours or something like that. I mean, depends. If you talk to some people, they'll laugh at me. That's not so easy, but At the time when we were looking at this, Gregor Weiss, who was back in Innsbruck at that point, had a student, Thomas Kelton, who was building an interferometer like exactly of those sizes. So they said, okay, we'll send that interferometer over and then we'll be able to do some measurements. So at this time, I was in Moncton back then at that point. So Sasha Agne, a student who was in Waterloo, started working on this experiment. And then I went back to help a few times with this experiment and with the data analysis. And so what we get, I'll just describe the setup a bit. So we produce photon pairs in this first setup, in this first crystal. One of the photons goes straight into the interferometer, the other one gets down converted. So we get the 3 photons coming in here, and then there's a beam splitter, and then there's this unbalanced interferometer. So these are just retroreflectors used to build everything, and then we couple back into fiber and detect photons on, at this point, we're using superconducting nanowire single photon detectors. And we see that for the single photon fringes, it's just basically flat. Similarly for the 2 photon coincidences. And then if we change any of the 3 phases in the interferometers, we get these nice interference fringes. Yes.
I'm just curious what kind of inequality you actually have to apply. Like, do you really need 50% visibility or 1% visibility? Or
yeah, I forget what the limit is. I think we did some work on looking at what a classical model would have to be, but I forget exactly what we did.
So in the end, do you just sort of use these indirectly as evidence that you have all the right correlations, or do you violate some particular restrictions?
I don't think I think we looked into inequalities and we ended up not like using that as like the fixed criterion. And I forget what the reason was that like made that hard to do for the 3.
The reason I asked is because you talked about needing a meter long path, which
Yeah.
for the vector resolution.
Mm-hmm.
And if you didn't do that, you could still get beautiful Branson fringes that just be under 50% visibility.
Yeah.
So how much that actually matters to you.
Yeah. I think we really want it to be in the like Branson stage. So in our case, like we can see everything and it's. Yeah, I'm not sure, but I know that in planning the experiment, we definitely planned the size of the thing before thinking about all the inequalities that we actually needed to look into and whether we were going to use that as like our final, like if the abstract was going to say we violated this number of inequality or if it was just going to be like, look at our fancy fringes. Yeah, I forget, but I remember we had a lot of discussions about what kind of model you need to be, because it's more complicated with 3 photons. Like with the 2, you can build like this classical models and say, okay, this is the limit. But I think with 3, it was more complicated, but I forget exactly why. So now I'll talk a bit about polarization entanglement. So polarization entanglement is nice for a lot of proof of principle experiments. Like it's just a degree of freedom that you can code qubits and then you can do measurements with it. You can do tomography, see what your fidelity is. It's a lot easier to use than energy time entanglement for practical applications. So all we need to do for that is we need to change or convert our sources to be basically entangled pair sources. So what's an entangled pair source? Well, one way of looking at it is something that if you send a horizontally polarized pump, it produces photons that are both horizontal. And if you send a vertically polarized pump, it creates 2 photons that are vertically polarized, and it does this in a coherent way. So we just cascade 2 different pair sources. And the setup that we built to do that is this one. So the first source is a Sagnac source. So there, the idea is that if the pump is horizontal, it's going to travel one way across here and produce one type of pair. And then if it's vertically, it's going to travel the other way and produce the other type of pair. And then we feed the 776 photons, nanometer photons from this source inside a mag center type source. So in this case, it's got 2 different PPLN crystals. And then so if it's a horizontal photon coming out here, it's going to get down converted in this one. If it's vertical, it's going to get down converted in this path. These waveguides that we were using were fiber pigtailed. So we have long fibers on each end, which is why we can't do a Sagnac or something like that, because we've got like 780 nanometer PMF. So that wouldn't work for the 1550 fibers traveling backwards. It also means that it's a fairly big interferometer, like a few meters of fiber. So we need to actively stabilize the phase. So we have a stabilization laser going in with the laser, and then we had this was mounted on a piezo that could basically keep the fringe constant throughout the experiment. And then at the end, we detect the 3 photons, and then we can do 3 photon tomography on this. So this was the first experiment we did where we had access to superconducting nanowires. So this was in 2013, before they were like the good ones were commercially available. So NIST actually came over for other detectors. Initially, they told us, "Hey, you've got these detectors. You have like a week." So I like planned all my work. I like had everything set up. And then in the end, we ended up having them for like 2 months or something. So we did just a bunch of experiments. And this was at the end of my PhD. So what would have been like 3 or 4 papers that we did, we just packaged it all and did this big paper where we did a bunch of stuff. So with the nanowires, that gave us a huge boost. So we went from around, this is in 8 hours, around 10 triplets per hour to getting around 600 triplets per hour. So it's a huge boost to our rates. It allows us to do full 3 photon tomography. So we need 27 measurements, keeping both outcomes. And we find that we have an 86% fidelity with a GHZ state. And then we showed that we could herald Bell pairs. So something that you can do with 3 photon GHZ states usually. So we just project 1 photon on the diagonal basis, and then the other 2, we show that they end up in one of the Bell states. And we also use those to violate a CHSH inequality. And then we did a Mermin inequality, and we did a Spetschlichny inequality. So we just did everything we could think of with these things. The downside with this source is that because we have that Mach-Zehnder, that really limits the fidelity that we can get. So our fidelity with the GHZ we wanted was about 86%. But then if you look in the details, we've got 11% fidelity with this state, so just the opposite phase. And our purity is quite low. So that really points to basically being a lack of coherence between HHH and PVV being the main limiting factor for this source. And there's 2 reasons. There's the fact that we have 2 crystals. They might have.
Just to be clear, that's when you try to make HHH minus VVV.
Yeah.
Or something.
Yeah.
Not that you can't do a good job on HHH.
No. We could just have to change the phase. No. This is just showing that like we don't have any like off diagonal. It's not like a rotation or something. It's really the lack of coherence between these 2 terms that's causing that's a limitation. And one reason is that we have 2 different crystals here. They're going to have they could have slightly different spectrums. So if that could cause problems with coherence. And then there's this active phase stabilization, which isn't perfect. So one of the first experiment that I started when I started in Moncton was doing a phase stable version of that experiment. So basically replacing the second source with a phase stable Sagnac source. We didn't want to mess with coupling into waveguides within the microscope objectives and stuff. So we still used pigtailed waveguides. We initially wanted to use waveguides that were pigtailed with photonic crystal fibers that are endlessly single mode. So they're single mode for both the pump and the down conversion. We ended up having a lot of technical issues. The manufacturer had to splice the fibers together. So they glued one fiber and then they spliced another one with a connector on. And that ended up giving us a bunch of weird reflections. So we kept getting these time-dependent signals. So in the end, we swapped to just use 1550 polarization maintaining fibers, and then kept them very short so that the 775 is reasonably single mode over the short distance. The downside, so that worked really well. We have good fidelities for both sources individually. The downside is that because we're now coupling light, these couplers P1 and P2 have to be optimized for 2 wavelengths. We weren't able to do a very good job of coupling really well for the pump and for the 1550 as well coming out. So our rates are back down to the terrible regime. So we have very good visibility in the diagonal basis. So around 95% visibility, which is really excellent for 3 photon states. But we don't have enough photons to do a full tomography. But instead we used an entanglement witness. So usually an entanglement witness just tells you, yes, your state is entangled if you get the negative value. But this entanglement witness is nice because it also allows us to calculate a lower bound on the fidelity with a GHZ state. And the nice thing is with the GHZ state, you only need 2 measurements if you keep both outcomes. So you need 1 measurement in the computational basis and then 1 measurement in the diagonal basis. And then that gives you a lower bound on your fidelity. So it's really nice for that. So these are the results. We get the visibility in the HHH and VDV bases, and then in diagonal bases, it's very good. So we calculate or this is negative, so we know it's entangled, but mostly our lower bound on fidelity is 96% plus or minus 0.05, which is actually, as far as I know, that's the highest fidelity GHZ state for a three photon state that's been reported. It's not really a fair comparison, because if the people who use like pulse sources and like use post-selection to create the state, if they were willing to sacrifice rates to get to our rates, they could probably get something similar. But in their case, they're usually trying to get, reasonable rates to do other experiments. So they're not really focused on that one number. Are there any questions at this point? Yes.
Is it possible to do kind of a waveguide version of the pair DBO that the polarization entanglement source? So you like periodically pull one section to do H2 in the second section.
Yeah, I know it's been done in bulk with long quasi phase match. I don't know if someone's done it. I think I know people have tried to do it in waveguides, but I'm not sure if it's been successful with like good fidelity. It's comparable to what you can do in bulk. But in print,
seems like it would help simplify it.
Yeah, for this in this case, yes, of course. If you can fabricate that, then yeah, it's like getting rid of this whole thing is way better. Yeah. But the other thing is you need to be able to do it with comparable efficiency. So there's a lot of literature about saying, oh, we've got these really highly efficient materials doing down conversion. And then if you go down to like the experimental results and you compare what their bottom line efficiency is, it's rarely up to 10 to the -5, which is what the best PPLN ones are. So like there's been a lot of work on like thin films PPLN, and then they'll claim like best conversion efficiency in lithium niobate ever shown, and it's worse than the commercial ones we can buy from HCP. So, but yes, like you're totally right. That's like the way to do it, like smartly for the like looking forward. That would be good.
I just had a question about the Bronson.
Yeah.
So what is the deformable mirror doing with that? After
Here?
Is that DM?
Oh, DM. Oh, sorry. DM is just a dichroic mirror.
Oh,
So it's
okay.
just splitting these two photons
Okay,
based on like
yeah.
1530, 1579. I guess. Yeah. Okay, so I'll talk now a bit about kind of, so everything up to now has been like, well, how can you create entanglement? And now we're looking at kind of other things that we could maybe do with these systems. The first being heralded single photons, and then I'll talk about photon pre-certification. So the idea with single photons, I mean, I think if you know down conversion, you probably know that it can be used to produce heralded single photons. So you've got a pair. If you detect one photon, you should have something that looks like a single photon on the other. It's not perfect. There's several limitations if you have loss. So if you've lost this photon here, then you're going to announce the presence of the photon, and then there's none there. If you have detector dark counts, then you're going to get a click here saying you should have a photon there, and then there's none. Or you can have double pairs, so you can have more than one pair that's produced. So then you'll say you have one pair, but then you actually have two. So all these things limit the quality of the single photons produced by heralded by down cascaded back, just down conversion. So our idea was, okay, what if we, instead of using just one click, we use 2 clicks here to herald the presence of single photons? Does this give us any advantage? And there's 2 ways of thinking about this. I could say, let's say I have this fixed source of heralded single photons. Would I be better to down convert those single photons to kind of get more information about, like, better knowledge that this photon is really there before detecting it? And I'll talk about pre-certification in another context later. Or you could think about it, if I have this fixed source, am I better off pumping it with heralded single photons? And will I get better heralded single photons out from that? And the way that we characterize this was looking at the heralded G2. So if you haven't seen these before, so the idea is that you take this heralded single photon, then you do a Henry-Brown twist measurement on it. So you're looking for coincidence between A and B. That should never happen if it's a real single photon there. You should never get a click at A and B at the same time. it should always be 1 in A and 1 in B. So just to get a kind of a feel for it, what you're hoping to get a lot of is these two guys, and you should never get a threefold coincidence. So basically, if this works as possible, you get a large denominator and a small denominator, and you get a G2 that goes near 0. In our case, this just gets generalized, where basically detector 1 just means getting a click at those two detectors. And since I'm talking about this, about heralded single photons, I should talk about frequency correlations, which is this is the paper I was mentioning earlier in response to Ephraim's question. So basically, they showed that by choosing proper pump bandwidth, crystal lengths, the tripartite frequency will show either full correlation, partial correlation, or no correlation. So there is that degree of freedom to play around with phase matching conditions, as you'd expect. To calculate what the expected heralded G2s are for this, we use the detector model from this paper by Bussière. This is from Nicolas Chita's group. And the idea is that you write down this vector that encodes all possible detector states and the probability of being in all of them. So if you know all your detectors are off, then you just have 1 here and then a bunch of zeros. If all your detectors have clicked, then you have a 1 here. And the idea is you take this vector here and then you write down matrices that show how the detector state will change based on having I photons in the mode, or based on having a certain number of dark counts or just dark counts based on all the detectors. And then you can just do a sum over the probability of getting I photons, then you can rebuild basically what kind of singles, pairs, treefolds, whatever you want are expected. So we did this in 2 ways. First, we assumed that we had perfect detectors doing the Henry-Brown twist measurements, so these AB detectors. And the reason we did that is that if you look at the literature for like experimental results, that's what people usually do. So let's say people have built like a quantum dot source of single photons. When often in the abstract, they'll report a G2 that factors out the dark counts from their detectors here, if it's significant. And I think that's totally fair, right? They don't care about the detectors, they want to characterize their source, so it makes sense to factor that out. So to be fair, like, okay, let's do that. Let's see how SPDC compares with CSPDC. And what we find is that with SPDC, if you go to higher rates, you get a bad G2 because you've got too many accidental coincidences. And then as you go to lower rates, then it kind of flattens out. And the reason that it flattens out is that because accidental coincidences, dark counts at these detectors start basically telling you have a photon and you don't actually. And the rates of single photons produced are too low compared to what your dark counts are. Whereas with cascaded down conversion, it goes much, much, much lower, which would give you the impression that you can get a much better heralded G2. However, I don't think this is really fair in this case, because you can't really get, like, you'll never do a measurement like this without having real detectors.
This is theory.
Yeah, this is theory. And yeah. This is all theory. We were hoping to do an experiment, but it ended up being all theory. Like, you'll always get some clicks here. So it kind of makes more, and because we're comparing SPDC with CSPDC, we can let's give them the same detectors and then see how it compares. And there, what we have is that with normal SPDC, as you go to lower rates, you get a better G2, but then eventually you just get dark counts. You just have nothing left. So your G2 just goes up really high. With CSPDC, though, then you can get a bit lower and it stays low for a long time because it's really unlikely that you get a pair of dark counts on those two detectors at once. So it ends up that that's really the factor that we're getting a gain from. So you do get an advantage. Is it really significant? People who tend to use like maybe if you were doing like a metrology experiment for some reason and you wanted to have like the optimal G2, this could be useful if you're willing to give up rates. Or maybe for some reason you want like a stable G2 that's stable for rates. I don't know if that would be a situation someone could find themselves in. But yeah, it's not, I don't think this advantage is so significant that if I had someone who was doing heralded single photons, I'd probably tell them get better detectors. And that's what's going to help you more than trying to do it in cascade. As I said, yeah, we were hoping to do an experiment, but the problem is that like we really like to show these trends and stuff. The problem is that you need this fourfold measurement. And it's just so unlikely that you get that in the interesting regimes that we'd be like basically only working in this regime where you see no difference. So it ends up not being very interesting in that case, unfortunately. So we did the theory, but I forget how long we would have had to wait to get like that one fourfold. It was like probably weeks or something like that.
Well, so you'd really find zeros with huge error bars.
Oh yeah, exactly. But that's what does that mean? Like, yeah, we never see it fourfold. Okay. And yeah. So now we'll talk a bit about the last application I want to talk to you about is photon pre-certification. So this is proposed in this paper by Cabello and Scariano in 2012. So before there had been loophole-free bell tests. So their motivation for this paper was, how can we do a loophole-free bell test, given that we always have like large transmission losses? So now in 2015, of course, people did loophole-free bell tests without doing this, but this is still kind of relevant if you want to try to do something like device-independent QKD over long distances, for example. So the idea is that if Alice sends a qubit to Bob through a lossy channel, she can't violate a bell inequality free of the detection loophole because there's been too much loss. But what Bob can do instead is take this photon, downconvert it, and then take its quantum state and transfer it to a single photon over here, which is labeled as psi certified. And then the other photon just acts as a flag, confirming the presence of this photon pair. So the claim is that if you only do your bell inequality after you've had this flag, then the efficiency that you need to care about for the detection loophole is the efficiency between this when the split happens and the detection. So you basically factored out all this lossy part of the system here. Now, this looks a lot like what I've been showing you for this whole talk. We've got a single photon that gets downconverted. So it's kind of the setup that we have. So we performed an experiment to do this. So we've got a PPK2 crystal producing a photon pair, one photon, sorry, not there. Yeah, over here, we just produce a heralded single photon here that we prepare in a certain qubit state, and then we send that inside these two PPLN waveguides. And then we combine these on a polarizing mute splitter, and then we use a wavelength division multiplexer to split up this based on wavelength. And then our flag is detected at one of these two detectors in the diagonal basis. So if we look at what this is doing, it's taking the qubit from the input here. So it's taking this qubit and then transferring it to this untangled state, alpha HH plus beta VV. This is not ideal because we'd like the qubit, we'd like the state that's here to be encoded only on the signal, not on the flag. And instead we have this entangled state. So if we measure the flag in the diagonal basis, though, then we see that the signal is left in the correct state. But if we measure anti-diagonal, then it's left, there's a phase difference. So we can correct for that. We just need to do some feed forward. So we've got a Pockle cell here. So based on whether we get a click at D1 or D2, we do some feed forward and apply phase correction if needed. And so what we find is that if we herald on D, we get exactly the correct state. If we herald on A, we get exactly the wrong state. And then if we do the feed forward, then we always get the correct state. Now, how well does this work? You can see here we've got experimental points for direct transmission for a comparable system, and then here are the pre-certified. So it's always worse in this case. But the main reason it's worse is because of dark counts at these detectors in this case. There's just too many dark counts at these detectors, which means that most of the time when we're saying, yeah, we've had a single photon, we actually don't, and we'd be better off just not doing the whole thing. But that's like more of a technical thing related to these detectors. So if you switch to detectors that have, say, we had around 300 dark counts per second. If we switch to 1 dark count per second, then we're already better than direct transmission. And if we go to 0.001 darks per second, which could be feasible for certain types of detectors, then you're better for basically, you can go up to, I think, 35 dB, and still you could, in principle, do a violate the detection loophole. So that's one issue with this. Another efficiency is the heralding efficiency between the PDC and this. So in this system, because of the way we're coupling photons out of this waveguide and the fact we go to the Pockle cell, there's no way we'll do like over 60% detection efficiency. So in this system, that's not even linked, but we know that in principle, there's no reason why you can't get high coupling efficiency from PDC to this detector. And the other limiting factor is just the efficiency of this PDC process, right? So if we're using PPLN, it's 10 to the minus 6. Even if you could conceivably do this, the fact that you're reducing your signal by a factor of 10 to the minus 6, that's going to really harm you if you actually wanted to use this for something like this. So we'd like to have improved SPDC efficiency. There's many ways of doing that. So we're interested in looking at like novel materials that could improve. But we wanted to do an experiment looking at a different approach, which is to build a cavity. So initially we wanted to build, well, no, we said we're thinking, how can we improve SPDC efficiency? One way is to just put your crystal in a cavity. But if you put it in a cavity, then you get a very narrow acceptance bandwidth. So that doesn't work for us in our experiments. So instead, we figured to do this kind of, I hesitate to call this a cavity. It's kind of like a switchable delay loop, where when we have a single photon, we activate a switch, which allows it to come in to this loop. And then we close the switch immediately after, so the photon gets several opportunities to be down converted. And so we did some theory to look at what the efficiency is. And like there's a bunch of other factors you need to take into it, but basically the main thing is basically just 1/1 minus alpha, where alpha is basically the probability that you make it through the loop. So if you have a 90% transmission efficiency through the loop, you get a factor of 10 improvement in rates. Yes.
Is this fundamentally different from just having a bunch of PPLs or whatever?
One after the other? If you have them one after the other, then you start like narrowing your acceptance bandwidth. And in this case, because our loop is much larger than all.
You could outcouple after each one, right? So there's no appearance between them. So you're not
Yeah.
no longer PPLN. You're just
So what's the difference between two PPLNs that are like spaced out a bit? Yeah, okay.
I think that's actually the same.
No, yeah, I think you're
just unfold.
Yeah, I think you're right. I think that could be a way. I mean, it's a factor of 10 more expensive because you need more crystals, but no, I think that's right. But there might be some way of doing it like, I don't know if people have looked at some like integrated device where you've got like periodic splitting into a different mode for your down converters so that you don't get like the coherence. Sorry, do you have a question?
I was gonna follow up. Would that be under the assumption that those, let's say you want 10 round trips, that each of those different devices are perfectly matched with each other? And then they would also have to have some coherent with one another as well.
Well, I guess the point is to avoid.
Yeah, he was going the other directions.
Because like one of the reasons we don't just make your triplet a meter long, when that makes your down converting bandwidth very slow.
So if you have multiple crystals though, and they would all have to have matching phase matching conditions, well, so would that be realistic?
I mean, people do that. But anyway, I think.
Yeah, I mean, there's definitely like, yeah. If you're like in this case, we're just looking at doing it like without, like we're not even caring about the entanglement. But yeah, if you care about having your qubit pre-certified, then you need to care about having, it needs to be done coherently in that sense. Yeah. So this is the schematic of the experimental setup. So in our case, we have a Pockle cell that's triggered by a single photon, like just an APD detecting this first photon. And every time this photon, we get a click here, then we activate this Pockle cell. So this photon comes in and is horizontally polarized to come into the cavity and then becomes vertical and then just kind of goes around this several times. And then we detect our photon triplets based on this. The results look like this. So in our case, this was just a proof of principle experiment. So our loop efficiency is quite bad. So we only have like 20% efficiency, mostly due to these pigtailed fibers. But we can still see the effect where we get basically a triplet signal after a certain bin. And then after one loop, we get a second one, and the third loop, we get a third one. And we see that the scaling works as we expect in terms of the loop efficiency. So this is published by just this year. So in principle, the way that you could conceive this is that Alice sends this code on to Bob, and then Bob can basically have a fast switch In this case, you wouldn't do it. So in our case, we're using the signal to activate the switch. Ideally, you'd use a pulse pump. And then you would just activate the switch basically on a clock. And then Bob can just he knows when Alice's qubits are about to arrive. He just activates this, and then you get basically an improved, like many chances of getting a pre-certification. And then your pre-certification, your flag comes afterwards. So it doesn't matter that you're on several different like time bins, other than like you're getting more noise. So that has to be taken into account. Yeah. And just some future work that we're working on and related to this. So of course, we're interested in materials with higher nonlinearities. We had some interesting talk with John about that this morning, and hopefully some other ones today, because basically for a lot of applications, the SPDC efficiency is not that important because you can always just compensate with your pump. We can't do that. So for us, any kind of improvement from that 10 to the -6 and the -5 regime could really expand the amount of things that we can do. One thing we're looking at is spectral filtering to get better source compatibility. So in all the experiments I showed, the spectrum from PPKTP is a bit too broad for the PPLN waveguides by like a factor of 2 or 3. So we're doing some experiments. So we do the filtering, but we don't filter the 775 photon going to the PPLN. We filter the other photon. So we kind of do filtering in the coincidence basis. So we're doing experiments to show that. And the idea is that basically then we can become kind of agnostic about the first source and being able to just filter it however we want, no matter what we're using. And another thing, so in the pre-certification experiment that I showed, so there's this feed forward step. And that was necessary because basically it's an entangled pair source that we use to do it. But there's nothing intrinsic in the scheme that actually requires this feed forward step. So we have an idea for a scheme that we can do this without needing pre-certification, where basically you would get like a separable state. So if H comes in here, you just get HH, and if B comes in here, you get HB. And the fact that you remove this need for feed forward means that doing this in an integrated way with your detectors really close to your source, that becomes a lot more feasible than with this feed forward. So I'll just mention, so a lot of this work started in Waterloo, and then we had collaborators from NIST, from Vienna on the first experiment for the idea, and then with Gregor I mentioned for the Franzen experiment, and then Christophe Simon collaborated with us on the energy time entanglement, and then my group who worked on these few experiments in Moncton. Oh, and Cabello for the pre-certification. So thank you for your time, and yeah, you guys have any questions?
What about just using a kind of deterministic single photon source plus the source?
I'd love to do that, yeah.
But
I don't have a deterministic photon source, so I need a collaborator who's got a deterministic photon source who wants to
and I guess how can you that or like
that. Okay, so I think it'd be fun just to do it, just show that you can. It unfortunately doesn't give you pairs on demand, right? I mean, there's like less on demand than before because then it's down converted. I don't know for the single photons. Like if you wanted to do, okay, I've got a heralded single photon when it's on my clock from my quantum dot or whatever, and then I herald the other one, that might be interesting because then, so in our case, I mean, it's still probabilistic, but there you're actually getting a click from your detector confirming the presence of the photon. So it might get slightly different statistics. So there might be something interesting there. But I think it'd just be cool to do it because it's a cool experiment to do. Yeah.
In terms of the spectral filtering, I was just wondering, do you need to do it by filtering, or wouldn't there be some way of tailoring the polling so that you could match the bandwidth?
Oh yeah, for sure. If you want to, so in principle, if we made the PPKTP crystals longer and then with like more tailored polling, then yeah, you could probably get it to be basically tailored exactly.
Or why did you do it by throwing stuff out? Well, I guess you don't lose.
So the thing is that it doesn't really throw stuff out because I should have just done it here. By filtering over here, we're limited by this detector as well. So we do have a bit of room on our pump that we can increase our pump if we want to. Anyway, in principle, in our experiment, we can't go quite all the way because then we'll damage our crystal. So, but there is a limitation. Wasting photons here is not as bad as wasting them here, so that's why we're okay with doing it. And like we have that crystal, and we kind of want to show that we can do it. We actually tried to do it in Waterloo like 10 years ago, and it just completely failed. I think the filters that we bought were just terrible and they didn't work well. So then we just quit. So then we're trying it again now. And the only problem is that we're expecting, based on preliminary results, we're expecting a 1.5 factor in increase in rates, and we're getting a 2.5 increase. And we need to confirm that's the case. And if so, try to figure out what's going on.
So if you look at base legal GHZ state source,
Yeah.
first question is, what's the rate at which you can generate GHZ states?
So this one, so I think you can kind of see it there. Oh, I didn't put the time in, but yeah, it's on the order of like 5 per hour, 10 per hour on this source. It was not great. The PPLN waveguide wasn't the most efficient, and then we had these coupling losses that really have compounded to make it worse.
Okay. My other follow-up question is, if hypothetically you can create many GHZ states per second, let's say.
Yeah.
Would it be possible to invoke some kind of a bell distillation protocol with your source of GHZ states? Or because you had mentioned before, one of the disadvantages of your previous work on it was that you need about 6 photons in order to distill bell pairs.
Yeah, so not my work, but like, so there's this result that shows that if you want to be able to combine 2 photon entanglement to be able to herald bell pairs, you need a 6 photon state, so you need 4 triggers to prepare 2, whereas in this case you only need to detect 1 and then you prepare 2. So yeah, in principle, you could in principle combine, if you have enough pairs, then you could store them while you're doing.
Okay. I have a follow-up question.
Okay.
But yeah, thank you.
Go ahead.
I'll say it. Think about it.
Maybe I could just ask on the last thing you talked about the possibility of eliminating that feed forward,
Yeah.
but that maybe I didn't hear properly. You were doing something with polarization on a chip.
Oh,
This
yeah.
is a
So
difficult,
yeah, so our first experiment, we're going to do it in bulk
okay.
using polarization, just to demonstrate the principle. If you want to do it integrated, then probably polarization is not the degree of freedom to use, and then you'd want to use mode or some other degree of freedom. And then then we have to think about exactly how we can do the same kinds of operations that we can do with polarization with that other system.
Yeah. Other questions? No further ones, then let me ask you to join me in thanking the speaker again.
Very much.
Very neat. I understand a bit more. I'll have to look at some of the papers, but yeah.
Yeah, it's very, very experimental time.